we're ready to start, and we will start with the talk of Guilherme Vedana, who will talk about sphere packings with forbidden distances.
So, good afternoon. Thank you for the introduction. I'd like to thank the audience for the attendance, and also thank the organizers for the opportunity to be presenting here. So I'm going to talk about sphere packings with forbidden distances. This is joint work with Felipe Gonçalves, my PhD advisor. And so the sphere packing problem asks the following question. What is the densest way of covering the Euclidean space with congruent and solid balls? For instance, here you have an example of a sphere packing. Here in the left-hand side of the picture, you have an example of a sphere packing in 2 dimensions. So this problem is solved for some dimensions. For instance, for dimension 1, the problem is trivial because we can cover the whole line with unity intervals. For dimension 2, the best packing, the densest packing is called the hexagonal packing. It was proved by Tour, and it looks like this packing here in the left-hand side of the picture. And for the dimension 3, the best packing is the so-called cannonball packing. It was proved by Hales, and it looks like this picture here, which is the intuitive way of the best way of stacking cannonballs, for instance. So formally speaking, a sphere packing, so a sphere packing P is denoted by X plus BD. BD is the Euclidean unity ball, and X will be your set of centers, the centers of the spheres, and you ask the following condition. For any 2 centers, you ask that their distance either is 0 or it belongs to, or it is at most at least 2. So this is saying to you that your balls can at most touch in the boundary. You cannot have intersection with non-empty interior. And you define the density of a packing the following way. So you will have your packing, a collection of unity balls. You take a d-dimensional hypercube centered at the origin, minus t et raised to d. You intersect this hypercube with your packing, with your balls. You compute the volume of this intersection, that is the d-dimensional Lebesgue measure, and you divide by the total volume of this d-dimensional hypercube. You compute the ratio, you send t to infinity, taking the lim sup, and this gives you a number which is by definition the density of your packing. And the sphere packing problem asks for the supremum of these densities over all sphere packings that you can consider in this dimension. So we'll have some spatial packings. For instance, if your set of centers is a full rank lattice of RD, we say that we have a lattice packing. And in this case, you have an easy way to compute the density, which is given by this R over 2, which is the radius of the balls you are considering, raised to the dimension, times the volume of the unity ball, divided by the volume of the lattice. That is the volume of the fundamental region on RD defined by your lattice. And here R, I'm calling the minimal non-zero norm of your lattice so that you can use balls of radius R over 2 to build the lattice packing. And if more generally, if you have, instead of a lattice, but you have a finite union of translations of your lattice, we have what we call a periodic packing. And well, it turns out that for the best packings dimensions 1, 2, and 3, they are given by, they came from a lattice. Dimension 1, the lattice is the integers. Sorry. Dimension 1, the lattice is the integers. Dimension 2, it's called the hexagonal lattice. Dimension 3, the face-centered cubic lattice. And recently, Viazovska and her collaborators, they proved they solved the sphere packing for dimension 8 and 24, proving that, again, in these dimensions, your best packing is given, again, by a lattice. And for dimension 8, you have the E8 root lattice, giving the best packing. And for dimension 24, the so-called Lich lattice. And just to mention, Viazovska was awarded the Fields Medal by her work. So I'm going to comment about the idea of the starting point of the idea of Viazovska work. So it begins with the so-called Kohn and Elk's linear programming bound, which was proved is a result from 2003, and it says the following. So you pick a function from RD, radial, L1, such that both the function and its Fourier transform, they are continuous, and you ask three conditions. The first one, you ask that there exists a radius r, depending on your function f, which is strictly positive, such that your function is non-positive outside this ball of radius r. The second condition, you ask for the Fourier transform to be everywhere non-negative. And the third question, you ask this equality here. But the important part, this is just normalization. The important part is that both these numbers, they are strictly positive. Plus some decay hypothesis on your function and the Fourier transform in order to apply the Poisson summation form. So pick a function satisfying these properties. Then the result says that for any packing P, you have that the density of your sphere packing is at most this number here, r over 2. This r comes from your function f, raised to the dimension times the volume of the unity ball. This is a very interesting result. So here you have the density of a packing, a quantity coming from the geometric world, or sphere packing. Here you have a number you computed from your function f that comes from the analytic world, and you have this bridge between them, is inequality. And what makes this bridge here establish the connections is the Poisson summation form. I'm going to prove this result just for lattice packings. So take a lattice packing, and when capital R is the radius of the balls. So you can apply some dilation, and you are not going to change the density of your sphere packing, so that we are going to apply a dilation so that the minimal non-zero norm of your lattice is small r, so that you can use the radius of your balls to be r over 2. And then we apply Poisson summation over your lattice, which is given by this equality here. And since every non-zero element of your lattice has norm at least r, so the function f at this point is non-positive, so you will have this upper bound. And since we assumed that your function f hat is non-negative, so you have this lower bound here. And then just rearranging terms and multiplying by r over 2 to the d times the volume of the unity ball, you get the desired result. And yeah, this proves the theorem for the case of a lattice packing. And for dimension 8 and lambda the E8 root lattice, Kohn and Elkis, they conjectured that the existence of a function f8 attaining equality here. So here you put your E8 lattice packing, and here you put this function f that they conjectured the existence, and you would get equality here. And observe that if you get equality here, you solve the sphere packing problem, and at the same time you find the best packing. And they conjecture the same for dimension 24 and the Lich lattice. And so what Viazovska and her collaborators did, they found the magic functions f8 and f24, and they solved the sphere packing for these dimensions, 8 and 24. And so the starting point was exactly this relation here, because once you put your magic function here and you ask for equality here, you have immediately some conditions on zeros of your function, the Fourier transform, and this is the starting point of the construction of these functions. So the sphere packing problem now, it's solved just for dimensions 1, 2, 3, 8, and 24. And the natural question that arises is, so can we extend Viazovska's construction for other dimensions rather than 8 and 24? Well, there are some constraints. The first of these constraints is that the lambda d8 and the lambda 24, they are There are very special lattices that we call even in modular extremal lattice that we will define in the next slide. And as we will see, they just exist in dimensions multiple of 8. And the second constraint is that the construction uses modular forms, and so you have, for instance, you have constraints on the dimension. It must be a multiple of 4, but you have other constraints. And so what is an even modular lattice? A lattice is called even if every squared norm is an even integer for any point of your lattice, and it is unimodular if its volume is 1. And in this case, it is integral and will be self-dual. And as I said, these lattices just exist in dimensions multiple of 8, sorry, and there are only finitely many of them in each dimension, modulo symmetries. For these lattices, the minimal squared non-zero norm has an upper bound. It is at most this. And if you have equality, then you call your lattice extremal. And it is known that even in modular extremal lattice, they only exist up to dimension 163 to 164. So here I have a list of some even in modular extremal lattice in the first dimensions. In dimension 8, there is just one, the E8 root lattice, which was proved to be the best packing. Dimension 16 will have 2. But it's proven that there is another lattice that is it's called Barnes wall lattice. It's not even in modular extremal, and it's proven that it gives a higher density. So these lattices are not the best ones here. Does not give you the best packing in this dimension. Dimension 24 will have the Lich lattice, which gives you the best packing. Dimension 32 will have more than 10 to the 7. But it's proven that they are not the densest lattice packings. Dimension 40, you have more than 10 to the 51. And, well, it's not conjectured if they are the best or not. And dimension 48, we have 4 now, even in modular extremal lattices, and they are conjectured. So there is a conjecture here. Each of these lattices gives you the best sphere packing in this dimension. And well, there is a causing problem of the sphere packing, which is called the kissing number problem. So you have your space RD, and you fix a unity ball, a central one, and you want to compute how many congruent balls you can put touching the central one. For instance, in R2, you can have the following. So they can at most touch. They must touch the central one, and they cannot intersect. They can at most touch in the boundary. And for instance, in 2 dimensions, you can see that this number is 6. And well, for this problem, dimension 48, they conjecture that the first shell of any of these lattices here gives you the best kissing configuration for the kissing number problem. So we try to extend Viazovska construction to dimensions multiple of 8, and try to prove that even in modular extremal lattice, they gives you the best sphere packing. So as I said, the first dimension after 8 and 24 that is conjectured to be the best is the 48. So we jump to 48 dimensions. And so we begin by trying to apply the Kohn-Elkes linear programming bounds. So, and we found some problems regarding the signs of the function and its Fourier transform. And so we needed to modify a little bit the problem and consider what we call sphere packings with forbidden distances. And so what is the definition of a sphere packing with forbidden distance? So you take a packing, and we say that this packing here, x plus bd, avoids this set A contained in this half line if for any 2 distinct centers of your set of centers, their distance does not lie in your set A. And so we call A the set of forbidden distances. We define the density of a packing in the same way as before. And well, this idea of forbidden distance is not new. It was already considered in several results in code theory. And just to see two of them, we'll have this one, Basaligo, Cohen, and Zemmour, codes with forbidden distance, and this other one with for authors, codes with given distances. And so, for this case, we proved the following results. So in dimension 48, you consider this set here, square root of 4/3, square root of 5/3, this open interval as your set of forbidden distances, and you consider all sphere packings that avoid this interval, and we proved that, well, any even unimodular extremal lattice in this dimension achieves maximal density among all sphere packings avoiding this interval. And moreover, if you have a periodic packing in R48, avoiding this distance and attaining maximal density, then actually this set of set of translations actually is just your lattice. You have just one translation, and you have a lattice packing, and after this renormalization, you get an even modular extremal lattice. Therefore, in the class of periodic packings, avoiding this interval here in dimension R48, the even modular extremal lattice, they gives you the best density. And the idea of the proof. So we proved an analogy of the Cohen-Elkins linear programming bound for this case of forbidden distance. And then we had to build the magic function, and it will look following the Viazovska construction, and it looks like this at the end. F of x is the sin square of this thing here, which puts the zeros at the place that you want, times this integral transform of these Gaussians, and this function here, well, this eta is the Dedekind data function. This psi and this phi, they are given in this way here. Here you have the basis vectors of the corresponding space of modular forms, and this C phi and C psi, they are the coefficients, the matrices of coefficients that you are going to multiply these basis vectors to construct your functions. Okay, so using this function and the version of the Cohen-Elkins linear programming bound that we proved for this problem, it solves that, it proves the theorem. And curiously, Boy-Valenkov and Sher-Kashin, surely this is the wrong pronunciation of the names, they proved 4 months later that so they considered a version of the Kissing number with forbidden distance, and well, in their case, they forbid what they forbid is some angular separation between the spheres, and they proved that, well, in dimension 48, the first shell of any of that for even in modular extremal lattice, they give you the best Kissing configuration for this version of the problem with forbidden distance, forbidden angles in this case. And I'd like to finish by talking a little bit about the one-dimensional problem. In the original problem, it is trivial, but now with constraints, it becomes extremely non-trivial. Here, it's more suitable to consider an equivalent formulation. Instead of looking at forbidden distance, you take the complement of the set, you look to the allowed distance between the centers of spheres. So let K be a bounded set in this half line, such that it contains the point 1. And we call that a packing is K admissible if for any two centers in your set of centers, their distance is either 0 or belongs to K, or it's larger than the supremum of K. And we made the following question. So, are there any periodic packing admissible, K admissible, attaining the maximal density? And so, for the particular case in which K is finite, we have an answer. If K is finite, then you have indeed an admissible packing, which is periodic and has maximal density. And I'd like to comment about the proof, the idea of the proof. So we built a domino set. I call the K. It's a set of ordinate pairs. The faces of the domino, we call the domino pieces. They belong to a finite set. And it is in such a way that if you consider any domino tiling, which is an infinite sequence W1, W2, W3, and here is understood that for consecutive elements, Wj plus 1, it's a piece of your domino set. So for any infinite domino tiling, you can associate a packing. And for any packing, you can come back and associate an infinite domino tiling in a one-to-one way, injective and surjective. And so instead of looking to packings, you can look at these domino tilings. And we also defined that kind of an idea of a density of a finite tiling, W1, Wk, such that if you send k to infinity and take the limit sup, we get a number which we define being the density of gamma. And it has a property that if you take the associated packing with your tiling, you have the quality of this density. So in this way, you can define the density of the infinite domino tiling. And to finish the proof, I will draw a picture. So we can stop looking at packings and you can look at the tilings. And the way I really like to see this is as a graph. So you have your set of faces, finite set. I will represent it as the vertices of a graph. And so call this W1, W2. And if W1, W2, this piece belongs to your domino set, I would join them. I would draw an arrow from W1 to W2. And in this way, you can build a directed graph. For instance, this thing here. And so the definition of the density works in a way that, well, it allows a very intuitive way of thinking about the problem. So imagine the vertices as if they were cities, and these directed arrows as they are roads, directed roads, and connecting the cities. You want to, each road has some traffic conditions, some qualities that you can have some average speed in each of these roads. And so you want to make an infinite walk in your graph, and you want to maximize the average speed. So each of the arrows, each road enables you can have some average speed, and then you want to make an infinite walk in your graph to maximize the speed. And for instance, suppose that you have an infinite walk. Because the graph is finite, you have one of the cities that is going to appear infinitely many times. Call it W, for instance. So from here to here, you have a closed path starting and finishing at the same city. And so what you can do is replace this by the best possible trip that you can do. That is, choose the densest, the biggest average speed. And so you do this here again, and then you get a new walk with a higher average speed than before. And in this way, well, your problem reduces to finding simple closed paths in your graph with the biggest speed, and this you can do because your graph is finite. And then in this way, you get the best travel you can do, the best walk in the graph. And then you translate to packings, and you find exactly the periodic packing with the density, the highest possible density. And, well, this finishes the proof. Thank you very much.